All right, so based on the overall structure of how vector calculus is working in 3D, we have this guess for something that feels like it ought to be true, that the surface integral over the boundary of a volume of a vector field ought to be equal to the integral of the divergence of that vector field over the interior of the volume itself. And we worked out an example of this and observed that yes, indeed, these two things are actually equal. And it seems for intuitive reasons, it seems like these ought to be the same thing because these seem to be two different ways of calculating how much the vector field flows out of the volume, right? So we have lots of reasons to think this is true. So that means it's probably worth spending the time to figure out if this actually is true. That is, we'll try to prove it. And as with Stokes' theorem and with Green's theorem, the strategy is to, rather than trying to prove this formula for a volume of any shape, prove it for volumes that have a very specific special shape and somehow use that the specialness of that shape to assist with the proof somehow, to let us do some calculations in the proof. And the special shape that we came up with is this capsule type shape. I called this a capsule type shape. So it's essentially, the sides of it are essentially a cylinder and the top and the bottom caps are graphs. Okay, so here's the shape we have. This entire thing is sitting over some region R in the xy plane. So the sides are vertical over this curve in the xy plane, and the graphs, here I've named the function, the top cap, I've named that, the function that is a graph of, I've named that f, and the bottom cap, I've named the function that is a graph of, g. So the goal is prove this formula for volumes with this shape. Actually, what we'll do is prove a special version of this formula for volumes of this shape, and then, as with Stokes' theorem, we can stick volumes with this shape together to prove our special case of this divergence theorem for general regions. But then, by decomposing the volume into special shapes in three different ways, we can prove three different versions of the divergence theorem that, when you add them together, give you the full divergence theorem. Okay, so we saw that happen with Green's theorem and with Stokes' theorem as well. Okay, so to get us started, let's just write out what these two things actually are. So this surface integral, so this is going to be so as we do this, remember that our usual notation for the vector field is to call the coordinate functions capital M, capital N, capital P, right? So, so for the surface integral, this is the integral over the boundary of V of capital M dot the normal vector d sigma. Okay, right. Okay. No, what I need here is capital M times 1, 0, 0 dotted with little n d sigma, there we go, plus the surface integral over the boundary of the volume of capital N times 0, 1, 0 dot normal vector d sigma, plus the surface integral over the boundary of the volume of P times 0, 0, 1 dot the normal vector d sigma. So this is just writing out this dot product term by term, right? The x term is here, the y term is there, and the z term is there. Well, when I say term by term, what I mean is entry by entry for the vector field f, right? If you add these three vector fields together, you get f again. Okay. For the triple integral, this is the integral over the volume of the divergence of f, that is partial m partial x partial n plus partial n partial y plus partial p partial z all dv. But instead of having all of these three in the same integral, we could split them up into separate integrals like this. So integrate all of these dv over the volume like this. And what we're actually going to show is that this last factor here is equal to this part right here, okay, for this special kind of shape. So whatever your whole volume is, you can decompose it into shapes that are these special capsule shapes. We'll show that these two things are equal for those special capsule shapes, but then you can paste your volume back together, so we'll know that these two things are equal on the entire volume. But then you can decompose your whole volume into capsule shapes instead of going in the z direction, going in the y direction, and that's going to show that this on those special capsule shapes, this integral with partial n partial y is going to be equal to this. And then, of course, you paste those special capsule shapes together back into the original volume. So then we'll know that these two terms are equal to each other. And then you do the same thing for the third direction. And then we'll know that the sum of these three is equal to the sum of those three on the entire volume, right? So as usual, we're decomposing into special capsule shapes and then or special regions and then putting everything back together. Okay, so what we need to do is work out what is each one of these things on this over this volume. So let's start with the surface integral. So we need to work out what is the integral over the boundary of the volume of p times 0, 0, 1 dotted with the normal vector d sigma. Okay, well, the boundary of v is equal to the surface S3, so I've named the top cap S3, I've named the sides S2, and I've named the bottom cap S1. So we can work out this integral over each surface separately and then just add them together. We do need to be careful about orientation when we do this, because remember, when we came up with this guess for the divergence theorem, we thought that this surface should be oriented outwards, right? So we'll have to make sure as we go that we're choosing outward pointing normal vectors for these surfaces. Okay, so let's do S2 first, because that one turns out to be the easiest. Okay, so when we work out this product, okay, if you look at this integral, well, what is the normal vector going to be along the sides of this region? Well, because the sides of this region are vertical, right? Because the sides of this region are vertical, n is going to be parallel to the xy plane. So in other words, n is going to look like something, comma, 0. But then when we take the dot product with 0, 0, 1, we get 0. So we're integrating 0 here. This entire integrand is just 0. So this integral over S2 is actually just 0. If you wanted to explicitly parameterize this surface S2, you could use, right, there's going to be some boundary down in the xy plane, and so you would have to use, I guess, let me write this boundary as x of t comma y of t for the boundary of the region that we're sitting over in the xy plane. The x coordinate would be x of t, the y coordinate would be y of t, and then because we need like a cylinder sitting above this boundary curve, we just have another parameter, right? So this parameterizes S2, and if you work out the normal vector, you will find that this coordinate right here is 0. Okay, so how about for S3? I feel like I numbered these backwards. Why did I call this one 3 and that one 1? I don't know. Okay, so for S3, that's the 3, we need to parameterize this surface, but remember we chose this special shape so that this the top surface here is a graph. So we can just use the graph parameterization. So for our parameterization, we can just choose u, v, and then f of uv. Okay, now we need to work out our partial derivatives so that we can take the cross product. So we get 1, 0, and then to save myself some space writing partial derivatives, I'm going to use this subscript notation for partial derivatives again, instead of writing out a million different partial symbols like this. So f sub u is partial f partial u, right? So the subscript tells you which variable we're taking the derivative with respect to. Okay, for the derivative, for the partial with respect to v, we get 0, 1, and then partial f partial v. And then for the cross product of ru and rv, we get so minus partial f partial u, and then minus partial f partial v, and then 1. Okay, now while we're here, let's stop to think about orientation. Okay, if we look at our picture, the outwards orientation for the top surface, oh, cat fight in the background, the outwards orientation for the top surface should be pointing generally upwards. It might also be pointing to the sides at some places, but generally upwards because it's the top surface. And this z coordinate is always positive, and so this cross product is pointing generally upwards, and so this is the correct orientation. So this is the one we want. All right, now that we have this, we can evaluate what is the triple integral of, I'm sorry, we're doing a surface integral, not the volume integral. That's going to come later. Sorry. Okay, surface integral. So we're integrating over the boundary of the volume. We're integrating over S3. Sorry. Integrating over S3, P times 0, 0, 1 dotted with our normal vector. So this is, oh, sorry. So we're parameterizing this integral. So we need to be integrating over the region in the xy plane, since the xy plane is the same thing as the uv plane because we're using the graph parameterization. So the region in the uv plane is the same as the region in the xy plane. So we're integrating over r. And right, this is where we put this cross product. So minus f sub u minus f sub v, 1, and then dA. dA here is du dv, so the area element in the uv plane. Okay, so when we work out this dot product here, so integrating over r, when we work out this dot product, well, these parts get multiplied by 0, and then this one hits that one. So 1 times 1 is 1 times p. So we're integrating p over this region. Okay. Oh, and this is, while we're here, let me be just a little bit more explicit about what this integral is. Remember, p is a function of x, y, and z, and so we need to plug in our parameterization. So this is the integral of p evaluated at u, v, f of uv. Okay, dA. All right. So that is the integral. Remember, that was over S3. So now let's do the surface integral over S1. So this is, first we need to parameterize the surface S1. Remember, S1 is the graph of G. Now when we work out this cross product, when we use the graph parameterization for this bottom graph and work out the cross product of partial derivatives, the orientation is going to be up again. we need to make it that so that it's going down. So we'll have to be careful about our orientations. So for this one, our graph parameterization is u, v, g of u, v. Okay. And then our partial with respect to u is 1, 0, g sub u. Our partial with respect to v is 0, 1, g sub v. And then the cross product of these two is, much like before, minus g sub u, comma, minus g sub v, comma, 1. And because this is the lower cap, right, remember we have this surface is below the rest of the volume, we need our normal vector to be pointing generally downwards, and so this one is pointing generally upwards, so we need to take the negative of this, right? So in other words, the normal vector, to get the orientation we need, the normal vector we need is RV cross RU, which is just going to be GU, GV, comma, minus 1. Okay, so now we can parameterize our integral. Remember, this whole surface is sitting over the region R in the UV plane, which is the XY plane. And we're integrating p times 0, 0, 1, dotted with this cross product, g sub u, g sub v, minus 1, dA, and again, this dA is the area element in the UV plane, so that's du dv. And then when we do this dot product, we get the integral over the region R of, this time we pick up a minus sign because of the minus 1 over here. Okay, so we get minus p of u, v, g of u, comma, v, dA. Okay, so now that we know the integral over S1, S2, and S3, we can write down the total integral over the boundary of our volume of p times 0, 0, 1 dotted with n d sigma, and what we got was the integral over the region of p of u, v, f of uv dA minus the integral over the region of p of u, v, g of uv dA. Okay, so this is for the surface integral. So now let's do the volume integral. And remember, for the part of the volume integral, we were going to calculate the integral over the volume of the portion of the divergence coming from p. So that's partial p, partial z, which maybe I should have written p sub z. Okay, dv. Okay, but remember, our volume has a special shape, so we can be a little more specific about what this integral is by writing down its bounds. Since our volume, our volume looks like this with cylindrical sides. It's sitting over a region R in the xy plane. So what we can do is in the xy plane, so I'll write dA again. So this dA is in the xy plane. Later we'll just relabel x and y as u and v, but for now dA is just the xy plane, so we're integrating over the region R, and then over any particular point in the xy plane, right, we have this sliver of volume above that point that is in our volume, and the z values, well, the lowest z value is down here, but that's the bottom graph, so that is g of x comma y, and the top of this sliver is on the top graph, and remember that was f, so f of x comma y. So that's the z direction. And we're integrating partial p, partial z. Okay, well now if you look at just the inside integral, our integrand is a derivative with respect to z, and then we're taking an antiderivative with respect to z to compute this integral. Well, the fundamental theorem of calculus says that we can just, the integral and the derivative undo each other. So what we're left with is, right, the integral on the outside doesn't change, but for the integral on the inside, our antiderivative can just be p. But we need to evaluate p at, from the bottom bound, which is z equals g of xy, up to the top bound, which is z equals f of x comma y. Okay, so when we write this out, what we get is the integral over this region of p evaluated at x comma y comma, and then z is f of x comma y, minus, and then plug in our bottom bound. So x comma y comma, and then z is g of x comma y. So this whole mess, dA. All right, well, if you look at this integral and compare that to our total surface integral, that's exactly the same thing. The only difference is what the variables are called, but the variable names don't matter. What matters is what the region is and what the area element is, but right, the area element is just d of each variable, and the region is the same region for both of these integrals. So this integral down here and this integral up here are literally the same integral, right? Only the names have changed, but the names don't matter. So we have proven that this formula, integral over the boundary of a volume of p times 0, 0, 1 dotted with n d sigma equals integral over the volume of partial p partial z dv. We have proved this on capsules, right? But then we can patch capsules together so that when we patch capsules together, we know that this equation is true for all volumes with piecewise smooth boundary, of course, as usual. Okay. So now we know that this formula is true for all volumes with piecewise smooth boundary, but then exactly the same argument, but with the variables changed around, is going to prove that the other two coordinate versions of this formula are also true. So right, n times 0, 0, 1 dot n, and then is equal to the integral over the volume of partial n partial y dv. So that's going to be true on all volumes. And then the third version is that the integral over the boundary of v of m times 1, 0, 0 dot normal d sigma is going to be equal to the integral over the volume of partial m partial x dv. So all of these are going to be true for all volumes with piecewise smooth boundary, and then when you add them all up, well, you get the divergence theorem. So that proves the divergence theorem is true for all volumes with piecewise smooth boundary, which is exactly what we wanted.